Transmission media. Fibre optics. Let's look at the properties of light waves. Well, it may seem obvious, but they travel at the speed of light, which is important because all electromagnetic waves travel at the speed of light. And because it's a wave, it must have refraction. It also has reflection, diffraction, dispersion, and interference. These are the properties of all waves, apart from the speed of light. To find out more, visit Physics Planet. So what is the speed of light? Well, light travels at 2.99 times 10 to the power 8 meters per second in a vacuum, or more bluntly, 300 million meters per second, which is pretty fast. So how can we use that to transmit? Well, let's first of all look at a few of the properties. More importantly, refraction. So let's take a look at what happens when light travels from the atmosphere to the surface of water. A beam of light will be travelling from all angles, but let's look at one angle in particular. So one travelling at this angle has an angle from the normal called the angle of incidence. Some will be reflected, but some will be refracted, or in other words, slowed down. So an example of this in real life is the straw in the glass of water. So we can see in this image of the straw how part of it looks out of place. This is because the light from the straw under the water is travelling slower than the light outside of the water. Further add to that the glass and more refraction will take place. We can actually use this to our advantage by sending light through a prism. The light then breaks down to its component wavelengths, seen as different colours of light. As they are travelling at slightly different speeds, they will be refracted more or less than the other colours. We also see this phenomenon when the sun shines through the rain to create a rainbow. So when our beam of light gets to a certain point, which we will call the critical angle, the light will travel along the surface of the medium. In fibre optics, this is a bad thing and needs to be avoided. But you can see this phenomenon by looking at the sky on a clear day. See how the blue light is refracted along the surface of the atmosphere. Gives the impression of a blue sky. This is known as Rayleigh scattering. To find out more about this, have a look on the internet. Make sure you spell it correctly. Reflection, on the other hand, is needed for fibre optics to work. So a beam of light comes in at an incident angle and is reflected off the surface. When the incident angle equals the reflected angle, we have reflection. So you may be wondering, why use fibre at all? Well, it has a wider bandwidth, and is several thousand gigahertz. There is no electrical current, so therefore no resistance, no capacitance or inductance. There is no crosstalk between cables. There is no electromagnetic interference. It's not affected by electrical motors, lightning, and it doesn't generate its own EMI. It's also resistant to environmental extremes such as heat, water and cold. It will also work in a wider temperature range. It's also safer, there are no voltages, and it's also lighter, so we can carry much more of it in the back of your truck or on a boat, for instance, and has a lot less loss, so we can go further before we need repeaters. But there are also a few reasons why not to use fibre. So there are some downsides, which is why we don't currently all have fibre at the home. Well, for one, the interfaces between the transmitting device and the fibre are very expensive. We have to use lasers, or LEDs, and light-dependent resistors. The tensile strength of the fibre is very poor compared to copper, and there is also a minimum bend radius. There is no electrical power, so repeaters will need to have copper fed to them. Bending causes losses. So the more bends there are, the less distance can be travelled, or it also limits the bandwidth. And the fibre itself is very susceptible to manufacturing defects. So if it's not manufactured correctly, we can have huge losses. Also, specialist tools are needed, not just a pair of crimps and cutters, as you would for a copper cable. So therefore, it's much more expensive to train personnel and to maintain. The fibre we use for communications can be subdivided into two types: single mode and multimode. Multimode is subdivided into stepped index and graded index. Looking at multimode, we can see that the core is 62.5 microns, where in single mode it's only 9 microns. This makes it lighter and much thinner. So how does the light travel down them? So in a multi-mode, there is multiple modes of light, but in single mode, as the name suggests, there is only one. From the side, it looks a bit more like this. But what does that mean? So for single mode, there's only a single path for light. It has a wide external acceptance angle. The cladding would be just air, but results in a weak cable. But the cladding does give it strength, but reduces the acceptance angle, makes it more expensive. Looking at multimode stepped index. So in stepped index fibres, the core and the cladding have a vastly different refractive index. The sudden change from core to cladding gives it its name. There's a larger aperture which allows more light to come through. However, this results in propagation delay. This is when multiple beams of light enter the fibre from different angles, and that each beam of light will reach the other end at different times. The distortion at the receiver is called propagation delay. And this limits the amount of data that can be sent down this type of fibre. Graded index, on the other hand, to reduce the number of internal reflections and delay, a different type of fibre was produced, called graded index. So instead of a sharp change in refractive index, a gradual or graded change was made to the density of the core until it reached the cladding. This resulted in less propagation delay than stepped index. So here we can see multimode stepped index, very sharp angles. However, the graded index allows for a more smoother transition of reflection and therefore less paths and less delay. So looking at the advantages and disadvantages. Single mode has a single path, so therefore there's no dispersion. Has a greater bandwidth, so a higher bit per second rate. However, it is more difficult to couple. The aperture is very small. It needs a highly directive light source and is expensive and difficult to manufacture. Multimode stepped index is cheaper to manufacture, easier to couple light, has a wider aperture, but it has several paths of light which leads to propagation delays. But graded index is a little bit more difficult to couple than stepped index, but it does have less distortion than stepped index.